Hey guys, my name is Brandon and today we're going to talk about combination problems. So what are combination problems? That's when we're trying to understand the number of ways that we can rearrange a set of objects. So let's get started. So before we can solve combination problems, I need to introduce to you what factorials are. Factorials are denoted as an exclamation point in mathematics, and the factorial of a number is the product of all positive integers less than or equal to that number. For example, 3 factorial is equal to 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1, and so on. So it turns out that this is actually equal to the number of ways to rearrange that amount of objects. So if you have 3 objects, 3 factorial is equal to the number of ways you can rearrange those 3 objects if each one is unique. In other words, none of them are identical. Let's move on. So in this example, they're asking us how many ways can we rearrange 3 distinguishable objects? Well, 3 factorial is 3 times 2 times 1, which is 6. And this, as you can see, turns out to be the number of ways that we can rearrange these objects. So moving on to our next example, how many ways can we rearrange 4 distinguishable objects? Well, 4 factorial is 4 times 3 times 2 times 1, which is 24. And that turns out to be the number of ways we can rearrange these objects. So let's ask ourselves a question. What happens if some of them are the same? In order to handle this, we need to call some of them indistinguishable items and others distinguishable. The difference is the indistinguishable items, if we switch those, is still considered one combination. And the reason why is because we cannot tell a difference between before it was switched and after the items were switched. For the distinguishable items, if we switch those, then we can tell a change. And so we consider that another combination. And as we saw in our examples, when we had 3 distinguishable items, 3 factorial was the number of ways we could rearrange those. And 4 factorial was the number of ways we could rearrange 4 distinguishable items. But if we have 3 indistinguishable items, or 4, or 100, the only way we can rearrange those is just 1. There's only one way to do that. And it's because there's only one configuration. It's not really the fact that you can rearrange it and you know you did, but the fact that once you're done rearranging those items, this still looks the same. So there's only one combination for it. So let's ask ourselves, what happens when we mix the two together? So here I'm displaying combinations for 4 items. And I want you guys to know that each one of the combinations that I'm presenting here actually represents 2 combinations. And the reason why is because 2 of the items are distinguishable. So all we do is switch those items and we're left with our other combination. What I wanted to show here is what happens if we temporarily treat our indistinguishable items as being distinguishable. And that's what's presented here, is just all of their combinations. Well, notice that if we go back to treating them as indistinguishable, these are 2 identical copies. So we have to divide the factorial of the total number of items by the factorial of the number of indistinguishable items. This gets rid of all of our duplicates. So expressing this idea mathematically, this is what we obtain. We take the factorial of the total number of items and we divide this by the factorial of the number of indistinguishable items. If we have multiple types of indistinguishable items, then we just divide the factorial of the total number of items by the product of the factorial of their numbers. So this last example ties everything together. We have n number of items. Out of those items, R of them are indistinguishable items number 1. The rest of them are indistinguishable items number 2. They're asking us to develop an expression that represents the number of combinations that we can rearrange these items. So using the information that we developed on the previous slide, we take the factorial of the total number of items and we divide this by the factorial of the number of indistinguishable items times the factorial of any other indistinguishable items. So in this case, that's n factorial divided by r factorial times n minus r factorial. And it turns out that this has actually been defined. It is an equation that exists and something that you can look up. It's called combinations. And these are the different forms for it. So you may have noticed that when we went from 3 factorial, which is equal to 6, to 4 factorial, which is equal to 24, that value rapidly increased. Well, 5 factorial is 120 and 6 factorial is 720. Just by increasing the number that you're taking the factorial of by one integer, the value that it equals is rapidly increasing. So by the time you get to 100 factorial, you're dealing with astronomically huge numbers. Eventually it gets to the point to where you can't even calculate it with your calculator. So we have to use something called Stirling's approximation. Stirling's approximation states that ln of x factorial is approximately equal to x ln of x minus x. This implies that x factorial is approximately equal to e raised to the power of x ln of x minus x. And of course you can write it in different forms as well. This is usually good when x is very large, but there's no real benchmark. The larger x is, the more accurate the approximation is. So for smaller values of x, you may want to use this approximation instead. It states that ln of x factorial is approximately equal to x ln of x minus x plus 1/2 times ln of 2 pi x. That's typically a better approximation for smaller values of x. I may go into a derivation of this if somebody comments and wants me to, but as for where I'm taking this video course, I don't really want to go too much into the rigorous part of this because it's not essential. It's a tool that you use for later things to come. And so that's it. Today you guys learned about factorials, combinations, and Stirling's approximation. Thank you very much for watching, and please subscribe.